Thank you very much for the invitation. I'm Alessia Caponera from University of Milano Bicocca, and I'm representing Italy today. And I would like to talk to you about this joint work with Victor Panaretos, Almos Stocker, Mathieu Simeoni, and Julia Fajou from EPFL in Switzerland. And the motivation of this work is related to climate and earth sciences applications, because we would like to look at processes defined on a spherical domain, and clearly if you want, we want to look at temperature on the surface of the earth or carbon monoxide on the surface of the earth. These are pretty much the setting in which we are looking for. So Jim Fang already introduced functional time series, so I'm looking to functional time series, so a collection of random function xt. The space in which the xt lives is some Hilbert space, for instance, the space of square integrable function on the sphere in our case, or some subspace. And these functions are assumed to be stationary in time under some definition of stationarity for Hilbert-valued random variables. One example, if we want to model, for instance, the time dependence, is a very well-known model, which is the functional autoregressive model. In this case, a functional autoregressive model of order 1, in which we have xt, which is our random function, epsilon t, which is a white noise function, so an Hilbert-valued white noise. And we have then this part which relates the observation, the function of the observation at time t-1 with the functional observation at time t. This rho is a linear and bounded operator from h to h, and since it is linear, it really represents the linear dependence between yesterday, let's say, and today. And so it's a very well-known model in the functional community. And just to have a look at the structure and to make some parallelism. So if your, let's say, H Hilbert space is just the real line, then you have the standard autoregressive model, okay, which with your xt, which is a scalar, your rho, which is a scalar, that multiplies x at time t-1. In the infinite dimensional setting, as I told you, we have instead an operator rho. And then in the finite dimensional setting, we can compute, we can define a lag h autocovariance function, autocovariance, which is again a scalar, ch for every h, and it's just, since we are assuming mean zero, it's just the expectation between the product at time t plus h and at time t. While here in the infinite dimensional case, we have a lag h autocovariance operator. So it's not a scalar anymore, it's for every fixed h is an operator. And it is defined in this way. Just, I don't want to go into details on this, but I would like to have a look at the connection between the operator rho in particular and the lag 1 and lag 0 autocovariance operators. So again, in the finite dimensional setting, we have this relation. Actually, rho is the autocorrelation of the time series, right? Because we have this relation that C1, which is equal to C minus 1, is equal to C0 times rho. So the variance times rho. And then rho is just C1 divided by C0. Here we have a similar relation, but actually we have two relations because we do not have any more equality between C1 and C minus 1, but we have this a similar thing. So C1 is rho applied to site C0. It's a composition of operators. And C minus 1 is C0 applied to the adjoint of rho. Okay? So the idea is that, so even in general, for the autoregressive model, rho is one of the leading parameters, and together with C0 and C1. Here, in general, for other models, we would like to focus on lag H autocovariance operators or autocovariance functions, depending on the Hilbert space we are looking to. So there is a connection between the operator and the function, the autocovariance function CH, which is defined as the expected value of the product of my function at time t plus h computed at u, whatever is the domain, and my function at time t computed at v, whatever it is my domain. So for instance, if we are looking at the sphere, u and v will belong to the sphere. So now, after this introduction, I would like to talk to you about the problem of measurement in FDA. So it is a general problem in the sense that we can think about, we can think that we are able to observe our functions on all over their domain. So for instance, if the domain is the, in this case, an interval, then we assume that we are able to observe all the function at every point. And this is, let's say, a classical FDA setting. And then there are some techniques that can be applied in this setting. Clearly, this is a simplification. Usually, one has something more like this one, so which is called a dense setting, in which you maybe observe your function only at some locations, maybe regularly on a regular grid and regularly spaced. And this is the so-called dense setting. In this case, you can simply maybe smooth the function directly if your grid is quite dense, and then work as if you are in the continuous case. But there is another point in which you can have maybe a sparse design. What does it mean for a sparse design? You have maybe observation for every curve observed at some location which are not on a regular grid. Maybe the grid is irregular and it is different maybe from curve to curve, and this is also sparse. So you have a very few locations. So in this case, you cannot really use the standard FDA techniques. So you have to work in a different way. So our focus will be on this setting, the sparse setting. And this is the very well-known model by Yao, Mueller, and Wang, in which our xt is not observed directly, is a kind of a latent process, and our observations are a noisy version of our xt, of our latent process, computed at some random location, called here the UTJ. So ETJ is a white noise, measurement error, let's say. The UTJ are random locations, for instance, uniformly distributed on the sphere. Xt is our latent process, and YTJ is our actual observation. And we observe, so we observe like n times point. So let's think about n different functions, and r points for every function, for every curve. We can also relax these are, and just asking that this is depending also on t. So we can have also different samples for curve per curve. So our xt will belong to some subspace of L2S2 in this case. So now our focus will be on the covariance, I told you before, on the covariance, autocovariance function at lag h. So if the lag is 0, so h is 0, we are looking at the covariance. So let's take, for instance, two locations at the same, so take one function, t is fixed, okay? So for instance, one sphere, and take two locations. Okay, at these two locations, we have two observations, one per location. Okay, so ytj at location utj, corresponding at location utj, and ytk corresponding to location utk. So we can compute the expected value of the product of these two observations conditionally on the location, and we can see that given our model, this quantity is equal to the covariance function, so the lag 0 autocovariance function, computed at the two location, plus the sigma square, which is the variance of the white noise. Then consider the case, so keep this in mind, and then consider the case h different from 0. So what does it mean? We look at two different time points, t plus h and t. Okay, so two functions. We take one location for one function, one location for the other function, and we look at their respective observation, yt plus hj and ytk. And then we do the same as before. We compute the conditional expected value. And we can see that this expected value of the product is exactly the covariance function at lag h computed at the two locations. So if our goal is, for instance, to estimate the lag h, whatever h is, autocovariance function, then we can think of this product and this product as, let's say, an unbiased estimator of the covariance or autocovariance at lag h computed at that location. So the idea to estimate CH is to consider the so-called row covariances. So we take the two locations and we compute the product, seen as an unbiased estimator of CH. If H is equal to 0, we have only to keeping in mind that there is also this term here, sigma square, and then the idea which appears only if we are looking at J equal to K, so exactly the same observation, so actually the variance of Y. So the idea is that we, for the case H equal to 0, we have just to discard the diagonal, let's say. So we have just to discard the cases J different from K. And then what we have, this is just an example on the K for 0, 1 valued functions, because for the sphere it's difficult to visualize. So we have all these locations, we have all these pairs of locations, and then for all the pairs of location we have a product. And then so we have this cloud of points of products. Okay, we said that the products are kind of unbiased estimator of CH, of the autocovariance. So the idea is that we can smooth this cloud of point to obtain an estimate of CH. If H is equal to 0, we just discard the diagonal. So this problem has been tackled by Yao, Müller, and Wang for the IAD case for 0, 1 valued functions, and also by Rubin and Panaretos in the stationary case, so in the time-dependent case, using local polynomial smoothers. So you have a surface which is the plane 0, 1, 0, 1, and then you apply local polynomial smoothers to smooth this cloud of point. So what's the problem with the sphere? The sphere is when you are working with sphere-valued functions, function defined on the sphere, then you have to estimate a function defined on S2 times S2. And we cannot really rely on local polynomial smoothers in this case. So the idea is inspired by Kain-1 is to use a spline type estimators. So our estimator is defined as this minimization as the solution of this minimization problem, in which here we have our products, okay, and the squared loss here, and then we add to this quantity a penalty. The penalty is defined as this norm. Okay, so eta is a penalty parameter, and this norm is our penalty. This is the L2 norm on S2 times S2 of this quantity here. What is this quantity here? What represent? It is a kind of derivative of P order applied to the function G. So a P derivative, let's say, of the function G. Clearly, this is an operator, so it's a more difficult object to handle. It's not just a simple derivative, but you have to think about this as a derivative, let's say, in the sense that we are imposing some regularity, and P really represents the regularity that we are imposing on the function G. For instance, indeed, this operator dp can be the so-called Laplace-Beltrami, the so-called Sobolev pseudo-differential operator. Indeed, this is the identity operator. This is the Laplace-Beltrami operator on the sphere, and we take the tensor of these two objects. Okay, so think about this Laplace-Beltrami operator on the sphere as a second derivative. Then you have P divided by 2, and then this is kind of order P derivative for the function on S2 times S2. And this allows to constrain our minimization problem to this space, actually, which is a Sobolev space, and which is also a reproducing kernel Hilbert space when P is greater than 1. This also it's a nice tool because we proved actually a representer theorem saying that the solution exists, it is unique, and it is also we can also compute it in a simple way. So back to this comparison, we estimated CH. If in a very general setting, we don't have to assume the autoregressive model. The estimation of CH is valid for every kind of time dependence and clearly under some ergodicity condition. Now, maybe if we want to assume for our XT an autoregressive model, we want also to estimate rho. And so here, it can be an easier task in the sense that maybe we can invert this relation and then we can take a plugin estimator. But here, the inversion of this relation is not really easy because C1 and C0 are bounded estimator, so you cannot really invert C0 because it will be an unbounded estimator. So this is an ill-posed inverse problem. So how you can estimate, for instance, rho. So here, as I said, you can just take a plug-in estimator. In the infinite dimensional setting, you have to be more careful. And we proposed a kind of estimator like this one, which is a version of a ridge estimator. Let's say here you can see a parameter alpha and the identity. So here you regularize this quantity to be able to invert this quantity. And we also proved some consistency result, which I'm going to show you. So we proved consistency and rates of convergence for C hat H, so for the estimator of the lag H autocovariance function, and so also of the linked operator in the Hilbert-Schmidt norm. And this is the rate. And also for the estimator of the autocorrelation rho, we obtained this rate of convergence, which is actually this rate to the power 1/4. And both under clearly suitable assumptions, but I don't have time to go into details of this. The nice thing is that we can see a kind of transition, phase transition in this rate, which is nice, because if we are in a really sparse regime, so if the number of points per curve is fixed, bounded by this quantity, then the leading term is this term, which is nearly non-parametric kind of rate, where here appears the regularity of the function on CH expressed by P. If instead, so and this is a really sparse regime, if instead R is allowed to increase with N, so maybe a kind of dense regime in which our observations increases on a single, so for increasing N on a single curve, then the leading term is 1/n, which is a parametric rate of convergence. So in this case, in the dense regime, the rate of convergence of these estimators is the same as for instance, the sample covariance estimator when you have a continuously observed function, which is 1/n. So if I don't know how much time do I have, if I can, I think I don't have so much time, but
yes, just continue. Don't worry, 2-3 minutes.
I'll just go very quickly. So to the real data application, which is just a preliminary application, so I don't have so much to show, so I will go very quickly. But the idea is that, for instance, in this sparse setting, as I said, we can think about climate applications. So there is this very nice project, which is the IAGOS project. So there are some aircrafts, and on these aircrafts, someone put some instruments that will measure during the flight, will measure some quantity, for instance, as the carbon monoxide on the air. So this is clearly is a nice setting in this kind of for this kind of problem. And with Almostoker and Victor Panaretos, so here we try to first estimate a mean, which is so especially because we do not expect that the mean is 0 in this case. So we subsampled the data, taking CO in parts per billion just at some layer or altitude, 4 to 7 kilometers. And we also subsampled the data daily. So for each day, we take 4 samples, more or less. And we estimated, this is the mean estimation in log scale, in log 2 scale of the carbon monoxide level. So we first estimated the mean, and this is the result. And then we subtracted the mean to estimate a covariance function, a covariance operator. And Clearly, it's difficult to represent the covariance functions since it's on a four-dimensional space, S2 times S2. So we just took the eigen decomposition, and this is the main direction, so linked to the larger eigenvalue sigma 1, and the related eigenfunction E1. And also we can obtain the autocorrelation estimator. Actually here the prediction, because it's the autocorrelation estimator applied to xt, so it's a prediction here plotted, and again we took the main direction, let's say here, and you can see here this quantity f1 plotted, determining the Heffet sites in the first component of the singular value decomposition in this case, and lambda 1 G1, which is the effect direction of the first component here, you can see. And as I told you, it's just a preliminary result, and we are working on it and also another application. So just to wrap up, we introduce a non-parametric estimator for the lag-H autocovariance functions without assuming any form of isotropy in the space, so only stationarily in time. So we actually are estimating an anisotropic covariance function. We developed during asymptotic result for the time-dependent setting. Kind 1 just did it for the IAD case for 0-1 valued processes. So our result, it's really the time-dependent setting, not just the spherical domain. And we obtained the autocorrelation estimator and the rate of convergence, which is the very first rate in this sparse noisy setting. And we also extended this work on compact two-point homogeneous space in the short paper of this conference. And clearly, it's nice because of the climate application that we can do with these tools. Thank you for your attention. These are some references.
Thank you, Alessia. Great work, naturally. I open the floor to the questions. Congratulations. I briefly start with mine, hopefully others join. In the solution to the ill-posed inverse problem, you used a reach estimator. Is it possible to use anything other? I'm not sure, but Tikhonov, Galarkin, so some other solutions I think are used in such cases. What would happen if any other estimator would be used here?
So it is a Tikhonov regularization. It is the solution of a Tikhonov regularization.
Sure. But is it possible to use any other estimator here?
Clearly, I mean, clearly you can. There are also other kind of estimators which are proposed in this case. I mean, in general for the autocorrelation operator. So the fact is that somehow. So mainly people, for instance, start from, again, this relation, and then maybe they truncate the operator C0, and then they did some plugin for the truncated version of C0. The fact is that that results relies first on the setting, in the sense that they are related to the standard FDA setting. These are results for when you really are able to look at the function, at the wall function. While here, the nice thing is that with this approach, we can be very, very general. So we just need an estimator for C0, an estimator for C1 or C minus 1, and the rate of convergence of them, and that the result follows. So the fact is that since you just need that, you can be in every kind of setting. So whenever you have an estimator for C0 and C1. So for instance, in the sparse setting, we obtained some estimators. We just plugged them on this quantity here, and then we obtained directly the rate of convergence of rho hat computed with respect to that estimators. So it is valid also in the sparse regime. So the nice thing of this is that it's a very, very general result.